So let's briefly finish this last part of the third proof of bounded Shumanovich upper bound on even extremal numbers of even cycles using Sidorenko's conjecture and repetitive use of Cauchy-Schwarz. So this is the upper bound we want to prove. The idea is the following. If there's a injective C2K homomorphism, we are done. So we may assume that most of the C2K, all the C2K homomorphisms are degenerate. And when we talk about degenerate ones, we first look at the largest degenerate homomorphism, meaning that two vertices get mapped together. And it's not hard to show by a application of Cauchy-Schwarz that this C2K minus 2 with dependent edge is the dominating term among all largest degenerate homomorphisms. So we may then assume that this C2K minus 2 with dependent edge has the same order of magnitude, occupies a positive fraction of all C2K homomorphism. Then we saw last time. What we see today, we'll see today is to use Cauchy-Schwarz repeatedly to then show that not only is CK minus 2 with dependent edge roughly the same as C2K homomorphism, but also you can keep going down the ladder to C2K minus 4 with two edges, all the way down to full cycle with all these edges, and then at the end, when you merge this two full cycle, you will get the K star. The final contradiction coming from the Sidorenko's conjecture for even cycle. We know that for even cycle, we should have this many homomorphism for C2K, but on the other hand, we just proved that KH star has roughly the same as C2K in terms of homomorphism count, but our graph is almost regular, so it's easy to bound the number of homomorphism of Sk by n times the maximum degree, which is up to this constant, is roughly this quantity. If you then compute, we will get an edge density bound from above the desired one. We saw an illustration, we started an illustration for A cycles. So for the first step, there are only two. For A cycle, it's relatively simple. There are only two largest degenerate homomorphism, either 6 cycle with dependent edge or 4 cycles sharing a vertex. So in this case, we apply Cauchy-Schwarz like this. This is like a picture illustrating Cauchy-Schwarz. Cutting along this line, then this is AI, this is BI, summing over all homomorphisms that look like this. Then squaring the red part is basically 6 cycle with a dependent edge. There's an additional bit here, but this is at most every homomorphism of this supergraph is a homomorphism of a subgraph. We have this sign inequality. Same as the other side, if you square the blue parts, you get C6 with dependent edge as a subgraph. So then we, because this is dominated by the 6 cycle, then we may assume all this 6 cycle with dependent edge occupies a positive fraction of C8 homomorphism. I should change this. Okay, so picking up from there, all we need to do now is to go down the ladder like this. Okay, so this is what we're going to do, and then do the final computation. So we've shown that we want to prove this. And have shown that number of C6 with dependent edge in G is roughly, by roughly, I mean, I will write this means equals to big omega of this quantity, right? This homomorphism of C8 in, so to be consistent, let me just try like this. The A cycle in G, this is what we show. And this means this. Okay, so now we're gonna compare 4 cycle with 2 pendant edge and 6 cycle with a single edge. We have to go down the ladder. This is also like a Cauchy-Schwarz. How do we do that? Oh, there's some announcements I want to make. Almost forgot. Before I forget, announcements. Several announcements. The first announcement is there is a change of time for the lectures next week. So first announcement. Next week, next Tuesday's class, so April 16 lecture, is gonna change to 1 day earlier. This is Tuesday. Let's do it on Monday. So April 15, Monday. Move it to April 15. That's the first announcement. So don't get confused. Same time, but just 1 day earlier. Second announcement, more important announcement is that there's a very low homework turnout. Only 3 people turning the first homework. I meant to make this announcement earlier, but I forgot. So there will be a score at the end. We will grade. We will give a grade to people who do homework, and there will be also a final exam. So for the final grade, homework will take up 50% of this weight, and the exam will take up also 50% of the weight. So I really encourage you to do the homeworks. And also for the students who are doing really well at with the homework and final exam, there will be a summer research program for undergraduate students and graduate students to come to IBS ECOPRO in South Korea. This would be tentatively will be July and August. July and August this year. So most likely we will have an early exam around mid-May, and then have the selection on students coming to IBS to participate this summer research program. Logistically, we will finalize the list of students by mid-May, and then the students can start applying for visa if you need a visa to travel to South Korea. Okay, and the ECOPRO, our group, will provide some financial supports towards the traveling, and also try to find accommodations for the visiting students. All right, coming back to this proof, right? So now we need to compare 4 cycle with 2 pendant edge and 6 cycle with a single edge. And same thing, we're going to do Cauchy-Schwarz. So let's recall Cauchy-Schwarz says, let's draw it on the side. Cauchy-Schwarz says, okay, if you have sum of AI, BI, AI, BI square is at most the sum of AI square times sum of BI square. Okay, no problem. So just like last time, how do we compare these two? Well, what we want to, how we're going to do it is we're going to show by Cauchy-Schwarz that the 6th cycle with a single edge square is at most the 8th cycle times 4th cycle with 2 pendant edge. So if I write this inequality, already we should start thinking how to make it like this form. So again, let's draw the picture. So the 6th cycle looks like this is a 6th cycle with a pendant edge. Okay, like this. So we need to sum over phi, right? Like last time, we need to choose some part to cut over and sum over the fixed part, and then we're going to square the other parts, color them. So here, we're going to fix this bit. We're going to fix this vertex and this vertex. Okay. This will be our phi now. It's just a homomorphism of 2 vertices, an empty graph with 2 vertices, right? And then the 2 colors would be, let's draw this red. This is the red part, and the blue part is the rest. Okay, so formally, how should we write it? If this is UV, then phi is all homomorphism of 2 isolated vertex to G. And then we should write A phi is the number of extensions of phi to a P4 homomorphism, right? You have some vertex, this vertex, and then a P4 homomorphism such that U and V are the 2nd and the 4th vertex. Such that these two are U and phi is here, right? This is phi. And similarly, B phi, so this is A phi. So B phi is the number of extensions of phi to a P5 homomorphism with endpoints U and V. Endpoints being the image of phi, more formally. So then we have the sum of A phi A phi, B phi square sum over all phi. So what would be the this is at most by Cauchy-Schwarz sum of A phi square sum of B phi square. Okay, what is sum of A phi square? So this left-hand side, this is just this guy, sum over all phi, square this, square that, is at most, square of this is at most sum of A phi square. So A phi square is, we have these two vertices, U and V fixed. So for the first part, A phi, we don't care about the blue part. Let's erase it. If you square it, we fix UV are fixed. So we have to find another red one like this, right? We need another one, square it. This is nothing but 4 cycle with 2 pendant edge. And here is 6 cycle with a single edge, right? Times, what about squaring the blue parts? Well, blue parts, we don't care about the red parts. Delete it. So we root it at U and V, find another P5 homomorphism with endpoints UV. So 1, 1, 2, 3, 4, 5. And lo and behold, this is a cycle. We proved the claim. It's one application of Cauchy-Schwarz. So good. So what did we prove? We proved that, let me rewrite this inequality. This shows that 4 cycle with 2 pendant edge divided by 6 cycle with a pendant edge is at least 6 cycle with pendant edge over 8. So it's the ratio gets larger when we go down the ladder of 2 consecutive ones. And as you might guess, the next thing to show is now if you collapse this one more time, you get a star. Star over the next one is larger than this. So this is the next thing to show. 4 cycle. Now you have 4 cycle. For this one, I will just draw the picture without writing the Cauchy-Schwarz with 2 pendant edge. And what will be the root? The root would be, we're going to root it on these 3 vertices. So our phi will be a P3 homomorphism. And this is our alpha phi, which is an extension of phi where we attach a P4 homomorphism with endpoints being these 2 vertices of phi. And the blue part is just this guy, which is the extension of phi. So this is B phi is the number of extensions of phi by adding a pendant edge to this P3 homomorphism, add it to the middle. In other words, B phi is the number of extensions of phi to a homomorphism to the star of size 3. So this square is at most the sum of the red part square. So for the red part square, we don't care about the blue parts. Let's delete it. So red part square, like this, right? And the blue part square, we don't care about the red part. Delete it, square it. Square it means just another one sticking out here, okay? So what does this mean? This just exactly means 4 with 2 pendant edge is square is at most. And this guy, recall, this guy is less than 6 cycle with a pendant edge because this is super graph of 6 cycle with a pendant edge. This edge is additional. So 6 edge with the, and this, the last one is just star of size 4. So summarizing it here, we get that this is at most 4 star over this. All right. So the final contradiction, we have final contradiction using Sidorenko is we're going to compare the most degenerate homomorphism. So this is the most degenerate homomorphisms of C2K with C2K. So this equals to, I write itself, times this telescopic sum. Oh, I write it wrong. Okay, we know, so 1 second, I haven't finished writing yet. This is decreasing sequence, right? So we multiply them together. And at the end, we multiply by an 8th cycle. So we will get the 8th cycle. These cancel, 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 cancel. Wait a second. What I'm doing here? So this shouldn't be there, right? This is equality. Cancel, 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 cancel. This equals to this. Okay. But what do we know? We know that we have shown that 6 cycle with a pendant edge is at least a positive fraction of, this is what we show at the first step. It's a positive fraction of 8 cycle. And we show that this is at least this guy. So this is also positive fraction. This is also another constant, constant times constant times constant. So this is at least some constant times, these are all constants, times C8. Okay, then here, Sidorenko says, this is at least n to the 8, p to the 8. But the maximum star is at most n to the 5, p to the, well, technically there's a maximum degree here, but more or less. Let me be a little bit lazy here, to the 4. And you compare these two, you will get that p is at most n to the -3/4. That's what we need. Any question? I think all you need to do is to remember this picture. It captures all the proof. All right? Writing all the detail is a little bit, if you write it rigorously, take some care, but The idea is simple. So to end this part, let me mention two conjectures that are still open. The first one conjecture is a conjecture I personally find it quite beautiful. This is rational Turan exponent conjecture. This is a conjecture by Erdős. It says that for any rational number, between 1 and 2 is a Turan exponent, meaning that we can find the bipartite graph H such that the extremal number of H is of order magnitude n to the r. Okay? It's quite pretty. It says that the Turan exponent, it really we can take it to be all rationals between 1 and 2. In particular, we know that it's true for 2 minus 1 over s for kst when t is much larger than s. So it's true for this number. It's true for 1 plus 1 over k. For even cycle, we know when k is 2, 3, or 5, that's tight. There are more numbers that we know, rational Turan exponents, but this one's still open. What's known is there was a breakthrough by Conlon, Book and Conlon, Boris Book and Conlon, who proved that we can indeed have extremal number of order magnitude n to the r for all rational r, but not forbidding a single bipartite graph, forbidding a finite family of bipartite graphs. True if forbidding of a finite family of bipartite graphs. There's a related conjecture by myself and my co-authors. So let me first tell you the definition of a one subdivision of a graph. One subdivision is simple. You have a graph. So let's say this is your graph. One subdivision just means a graph obtained from this graph by subdividing every edge of this graph, adding an internal vertex, distinct ones, so that this edge becomes a path of length 2. So that's one subdivision of it, of this. I will skip writing down the detail definition. Is the definition clear? One subdivision means for every edge of the original graph, we make it into a path of length 2, like this. All the new vertices are distinct. So this conjecture subdivision conjecture is by Kang, Kim, and myself, says that if we have the extremal number of some graph H, if you have an upper bound of n to the 1 plus alpha for some alpha bigger than 0, bigger than 0 and less equal to 1, less equal to 1, yes, then even including 0 is correct, but that's trivial case. So let's say alpha is positive and n most 1. Then we must have the extremal number of one subdivision. Let me write it like this, of h. So this is one subdivision of it. Must be upper bounded by 1 plus alpha over 2. Okay. What's interesting is remark, we prove that this conjecture, if it's true, will imply the rational exponent conjecture. Subdivision conjecture, if true, implies the rational exponent conjecture. You can examine all known cases, seems to be true. If you take H to be, say, even cycle, if it's even cycle of length 2L, we know that we can take alpha to be 1 over L, right? If you take one subdivision, it becomes even cycle of 2 times length. So it's 4L. Then the exponent becomes n to the 1 plus 1 over 2L, which is half of these. So it seems to be correct for all known cases. So now we're going to start the new parts, talking about extremal problems involving sets instead of graphs. So here we study extremal problems for family of sets so when you're talking about family of sets, what restriction we can put on different sets in this family? The only thing, the most common thing to put restriction to is how they intersect each other, their intersection pattern with various intersection pattern. Okay, and we've seen already some of these examples. For example, and what are those common intersection patterns? The containment is a very special type of intersection pattern. You have a set being a subset of another. For example, in Sperner's theorem that we've seen, we're going to recall it also later. We cared about largest anti-chain, means pairwise no set is contained in another. So this is one special type of intersection pattern. And for example, disjointness. Two sets disjoint from each other. Okay. Or intersecting. They're not disjoint. For example, E.K. Ehrlich-Corrado, we will see later. Okay. But these are the common intersection pattern. And recall, in the introduction part of this course, in the first 2 lectures, we've already seen some extremal set theory problem. The odd town, even town problem, where we put restrictions on the parity of, here we put restriction on parity of size of pairwise intersection, right? So you can really be characterizing this way. And Sperner's theorem. Sperner's theorem says if you have an anti-chain in A in 2 to the n, that means a family of sets that no one contains another, then, so let me remind you, that means for every A prime in script A is not a subset of A prime. Then the largest anti-chain for any anti-chain A, we have the size of anti-chains at most n choose n over 2, where the largest being the middle layer. We proved this, if you recall, by LYM inequality. LYM inequality says for every anti-chain A in 2 to the n, we actually have, if you sum over the elements, the sets in A, this quantity is at most 1. Okay. So today the first thing we will see is also about family of sets with intersection, restriction of intersection pattern. We have a family of pairs of sets, and we put restrictions in a bipartite fashion. We only put restrictions, we have two family of sets. We put restrictions for cross pairs. This is the Bolobash-Early set pairs inequality. This inequality says the following. We given sets A1 to AM and B1 to BM. We have this set comes in pair AI BI. On some ground sets, we do not put the restriction on the ground sets if they satisfy two conditions, that for pairs with the same indices, with the same index, they are disjoint. For cross pair with different indices, they intersecting. Okay. If ij not equal, they are intersecting. If they satisfy this, then the conclusion is we can bound the reciprocal of size of AI plus size of BI, choose size of AI, at most 1. Okay. In particular, if for all I in M, AI is of size A, BI is of size B, then all this is A plus B choose A, the same number. So we can move it to the other side, and sum over all 1 means the number of pairs in this family. We can get upper bound on M. Then M, the number of pairs cannot be more than A plus B choose A. What's surprising about this inequality is that if you look at this implication, we can bound the number of pairs purely by cardinality of sets in this system. We do not put any restriction on their ground set. The ground set can be arbitrarily large. The size of the ground set does not appear here. That's perhaps the surprising part for this inequality. The surprising remark notes that the size, so ground sets of AIBI do not play a role. So the proof of this, we're going to give 2 proofs. One is probabilistic proof, very similar to what we've seen before when proving LYM inequality. And we give another proof, dimension argument. It's similar to this odd-town, even-town. We can use it to prove a skewed version of Boloba's pair inequality. Any question about the statement? Okay, if there's no question, let's try to prove it. So let's remember the hypothesis. The sets comes in pairs, AI, BI, for the same index pair, so comes in AI, BI pair. For the same index, these two are disjoint. For different index, these two are intersecting. Proof, the probabilistic proof. Assume, let's give the name to its ground set. Assume the ground set of AIBI is the first n integer for some n. Just rename them if necessary. Now we're going to consider a similar trick we've done before, a permutation, random one, uniformly chosen from all permutations of n. So consider a uniform random permutation sigma n. In other words, we pick every permutation with probability, same probability, 1 over n factorial. We have that many choices. Okay. Now we're going to define the events. So we define an event Pi for every I from 1 to m, the events that in this ordering sigma, so sigma orders elements, right? 7, 3, 5, 1, 2, something like this. In this ordering, AI appears completely before BI. Let me draw a picture. AI comes completely before BI. Suppose this is increasing order from left to right in sigma. In other words, the maximum elements of AI is strictly less than the minimum elements of BI. And this max and mean is all with respect to sigma. I'm not writing sigma here. All right. So let's first estimate when sigma is chosen uniformly at random, what is the probability of these events Pi? Let's look at here. We might have some other elements, right? Some other elements. The events AI comes before BI only depends on the relative position of AI and BI. It has nothing to do with how their position compares to the rest of the elements. So Pi depends only on relative positions. So AI union BI, the elements in these two sets. In other words, the probability that AI occurs, events Pi occurs is what? How many ways to order all elements? Since we only care about relative position, we can forget about other elements. So just order these elements in these two sets. The total number of ways to order them is AI plus BI, these many elements. We range over all possible permutation. Take a factorial. Among all this possible ordering, we want AI to come before BI. That means we have this many choice to order them at the beginning, and then you can scramble BI at the end. So we have AI factorial choices to scramble them at the beginning and scramble BI at the end. This is the probability. And if you write this, that's precisely 1 over AI plus BI, choose AI. Start to look like this inequality here, no? So this is the probability of Pi, event Pi occurs. And that's the sum of the probability of all events Pi. If you want to show the sum of the probability of a collection of events is at most 1, you just need to show that these events are disjoint events. Meaning, if one event occurs, the other can never occur. Okay? Then, the sum of their probabilities are most 1. Suffices to show Pi, I in M are disjoint events. Then sum of probability of Pi is at most 1, which is what we want. So we need to show, in other words, if Pi occurs, Pj cannot occur. J not equal to I. Suppose they both occur. Let's derive a contradiction. So suppose we have, this is Pi. That means AI comes completely before BI. There are some other elements, I don't care. And this is the events A, Pj. It says that Aj comes completely before Bj, right? Looks something like this. Let's draw a picture. Okay. Very good. Let me redraw this a little bit. It doesn't matter. But to be consistent with my notes, let me try it this way. It's symmetric actually. So this is AJ. This is BJ. Okay. Suppose both of them occurs. Then what do we know? By hypothesis, we know that AI intercept BJ is non-empty. For different indices, they intersect. This is our hypothesis. That implies the minimum, if these two intersect, that means the minimum of BJ must be less than the maximum of AI. Okay, let's give a symbol. Let's say this is element 1. This is 1 should be less than 2 here. The minimum element BJ, if its size is 1, the maximum element of AI should be 2, bigger than 1. But PI implies what? PI implies all elements in BJ. This implies all elements in BJ is of order strictly larger than 2. Comes after that. And PJ implies all these elements are less than 1. AJ comes before 1, right? So let's write it here. This is less than by PI events. Let's say minimum of BI. This is bigger than by event PJ, the maximum of AJ. So what do we get? We get max AJ is less than mean BI. In other words, BI comes completely after AJ. So there's no way they intersect. That contradicts to our hypothesis that AJ also intersect with BI. Contradiction is AJ intercept BI is also non-empty. All right. Finishing the proof. Here I'll leave exercise to show that, come up with the example showing the tightness of this inequality. So whenever we see an inequality, we should always ask ourselves the first question, is it best possible? In this case, is yes. Exercise. Find an example. Showing tightness of Bol-Bush set pair inequality. Let's see a different proof of this with a strengthening. Different proof, the strengthening. Where is it? Here. How do we strengthen it? This is a skewed version, asymmetric version. We're going to weaken the hypothesis a little bit. skewed version of Bogomolov set pair inequality. How do we change it? We're gonna, again, we have pair of sets AI, BI. Such that, let's just directly write it like this. The sum of, such that the size of AI such that AI is of size A and BI of size B. Let's directly make it uniform, right? For all I. Actually, you can put inequality here, but let's just prove it for equality. And let's put inequality. Each AI is at most A, each BI is at most B. Intersection pattern is if same index, they are disjoint. When they intersect, not for distinct indices anymore, but for all indices I less than j, so a skewed version. For every I less than j, we have AI, bj intersecting. We have the same conclusion. This implies that the number of pairs is at most A plus B choose A, as in the original version. Here's a remark I want to make. Why I want to mention this skewed version. I mention this version because the proof, we only know one proof of it so far. This proof is by Lovatz and Alon Kalai. We only have algebraic proof of this skewed version by independently Lovatz and Alon Kalai. It would be nice to find a combinatorial proof. We don't finding a elementary combinatorial proof would be interesting. So this proof, we will use an linear algebraic structure called exterior algebra. There's no point introducing all this exterior algebra. Let me just give you the necessary basics about it. So if we have a vector space V, V is a vector space over some field K. Think of it as real vectors in Euclidean space, for example. Then the K is some natural number, exterior power of V denoted by K's exterior power of V What is it? It's just a vector, another vector space. It is a vector space spanned by elements of the form x1, this is just a formal symbol, wedge x2, wedge dot dot dot, wedge xk, where each xi is an element, is a vector in our vector space V for all I in K. Okay, so you take this formal product, wedge product of K elements in our original vector space. Use this formal product to span the vector space. But we have to quotient out something such that x1, x2, this element, quotient out those where 2 are the same, equal to 0 if xi equal to xj for some distinct ij in K. All right. So the basic property of this exterior power is that if, let's say, E1 to En, let's say the original vector space has dimension n, and E1 to En is a basis of the original vector space V, then a basis for this wedge exterior power, kth power of V, this new vector space looks like this. Just take the this wedge product of K bases, distinct bases, vectors in the original vector space. So I1 is wedge power EI2 EIK, where 1 is less than I1. So this is a set of bases for this new vector space. And it's easy to see. So the dimension of V, in particular, what it implies is that if dimension of V is n, then the dimension of this new vector space, the kth power of V, is what? We have to choose K distinct indices from all n basis vectors. So it's n choose K. This is the only thing that we have to use. Okay, and the other thing is the definition of this vector space. If you take the power, if 2 of the products in the power are equal, then you will get the 0 elements. So what we're going to do is we're going to map this AIBI somehow into a, we can visualize the these sets as map it to some vector space, the powers of some vector space, and show that this is the image of this map is correspond to linear independent elements in this vector space. So then the number m would be m most, then because it corresponds to m independent vectors in the vector space, is m most the dimension of that vector space. And these terms will turn out to be the dimension of that vector space that we will use. Proof of the skewed version. There's a little trick. We can assume every AI is A, every BI is B. Why? If it's less than A, you just add some dummy new points. You add some dummy new points to every set. Adding new points, and these new points are all disjoint, will not affect the intersection pattern. So we can always fill them up to A and B size by adding distinct new dummy elements may assume each AI is actually of size A and each BI is of size B. And let's assume, give a name to the ground set. N is the ground set, meaning the union of all AI, BI. Now, what's the vector space we're going to make use of? We just use the traditional Euclidean vector space. So let V to be the Euclidean vector space of dimension A plus B. Okay, and then in this vector space, we're going to choose n vectors in general position. N is the size of the ground set. N vectors V1 to Vn in general position. What does it mean in general position? In other words, every set of at most A plus B of VIs is linearly independent. Okay, we can choose as many as we want in general position. All it says is that if you pick at most A plus B points here among these, they are linearly independent. Okay, now we are all done with the setting. We're going to do this mapping. We're going to map what? For each, here's the map. For each I in M, we have AI, BI, right? We're going to let, how do we map AI? We're going to let YI be an element in the exterior power of V, this choice of V. What will be the element? It's the wedge product of all elements J in AI. So remember, N is the ground set. AI is a subset in here. BI is a subset in here, right? So this is a set of indices. Think of this N as a set of indices. Now you collect all the indices, you look at the corresponding vector in general position, Vj, take their wedge power, okay? This is an element, we take how many elements, power of how many elements? 8 elements. So it's in the 8th exterior power of our vector space V. Okay. We do similar things for BI sets. This is the wedge power of all indices in BI. You take the corresponding indices, their power. So this is in the Bth exterior power of V. No problem. Okay, now what we're going to do, we have to translate the hypothesis that AI, BI are disjoint and AI, BJ are intersecting if I less than J. How do we translate them? Well, recall the hypothesis. AI, BI disjoint, if they disjoint, all these VI, VJ, VK will be distinct elements. If you take the power, if you take the wedge power of YI and ZI, it will be a power of A plus B elements, but A plus B distinct elements in VI. They are linearly independent. So this is non-zero. This is the element, first of all, in A plus B, it's power of B, right? It's non-zero. That's the first inequality. For every I less than J, we know AIBJ is non-empty intersection. This implies now consider the corresponding wedge power, YIZJ. They are intersecting means in YI and ZJ, one of the components of the power are the same elements. Remember, the property of this vector space is if you take the power, two elements are the same, it becomes zero. So for all I less than J, this guy is again an element in this A plus B's power of V, but it's zero. This is the second property. Okay. All right. So now it suffices to prove using these two that this wedge power y1 to ym in ym, they are elements in the A's power of V are linearly independent. Why this will be enough? Because the dependency of them will imply that the number of such elements can never be more than the dimension of this A's power of V. But what is the dimension of A's power of V? Recall, if you take the kth power, the dimension is the dimension of the original vector space. Choose the power k. The dimension of the original vector space is A plus B, clearly. The power here is A, so the dimension of this eighth power is A plus B, choose A, which is the desired inequality that we want. How do we prove these are linearly independent? Suppose they are not. Suppose we have some alpha I scalar multiplied with yi and sum them out equal to 0. What we need to show is all these alpha I are 0, right? We need to show then we are done. They are linearly independent. So fix I in M. What do we know? Well, we know 0. If you take the wedge power of 0 with any elements, you will get 0. This follows from the basic property that if you take the power of an element with self is 0, you can derive this. If it's not clear, try to prove it yourself. So this is simple. Now let's expand this guy. Let's replace this 0 by this, right? We know 0 equals to the sum of this. So this equals to alpha 1, y1 plus alpha m, ym, wedge power zi. But this wedge power is a linear operator. So that equals to the wedge power of this Zi plus this equals to alpha 1 y1 wedge power Zi plus alpha m ym wedge power Zi. But what do we know? Remember, this I need to do it in order. So let's actually do it not for Z general Zi, but just for Z1. Okay? So what do we know? We know that sorry, I messed up with the order. I actually do it with the largest index, m. Okay, nothing's changed. I just multiply Zm with 0. Now replace 0 by this. Now expand this by linearity. Good. Now I'm going to use 2. Zm multiplied by anything yi, where I is less than m, will be 0. So that means all the previous term vanish. You only have the last term is not 0. So this, by the second equality, equals to ym. But by first inequality, by the first condition, this is non-zero. A non-zero vector times a scalar equals to 0 can only implies that this scalar ym is 0. So this implies ym is 0. Then it implies that we have one less term now. Right? The last term becomes 0. Then multiply by Zm minus 1, do it again, you will see that this equals 0, so on and so forth. Okay, I will not write the rest. You can show that all alpha I is 0. Any question? So let's see some applications of Bolobash set pair inequality. The first application is closely related to Sperner's theorem and LYM. You can use it to derive the other two. So the first I'll leave it as exercise to show that proof LYM inequality using Bolobash set pair inequality. That's the first application. The second application is about saturation number. We've seen it in the exercise, the homework problem, in the first homework problem. Now we can generalize it a little bit more. We can even define saturation number for hypergraphs. Surprisingly, for two-round problem, hypergraphs is really, really difficult. But for saturation number, hypergraph problem and graph problem, we can solve it in the same way, just using Bolobash set pair inequality. So this is saturation number. What's saturation number? Given, here's the definition, given a K graph, that just means K uniform hypergraph, and remember, K uniform hypergraph means you have this set of vertices like graphs, but the graphs is the edges of size 2. Now K uniform hypergraph here, let's say K equal to 4, the edges, the hyper edges is a set of size 4 instead of a set of size 2. Okay, that's just K graph. You have a K graph H. We say another K graph G is H saturated if G is sort of maximal H free. If G is H free, does not contain a copy of H, but adding any hyper edge to G will create a copy of H. Sometimes people also call this maximal H free. Same thing. Okay, then the saturation number of H is defined to be SAT and H, like the extremal number. Okay, you cared about edges in the hypergraph or graph where G has m vertices and G is H saturated or maximal H free. But instead of maximizing the number of edges, if you maximize it here, it will be the same as extremal number. We're going to do minimization. Okay, so it's important that this is minimization here. So here's an example. Okay, if you consider H is triangle, two uniform hypergraph, normal graph, by Mantel, we know the maximum number of edges is n squared over 4. But it's not hard to see that the saturation number actually just linear in n. All you need to do is, what's the extreme? To be maximal H-free, triangle free, you just need to consider this star. K1 n minus 1 star, right? If you add any edge, this guy is full, so you have to add in the rest. If you add an edge, you create a triangle. So the number of edges here is just n minus 1 edges. There's a huge difference between maximizing and minimizing. The exercise to show that we can solve this minimization problem fairly easily, but still, it's a very clever proof. But in terms of research problem, it's an easier research problem than the maximization problem, the Turan problem. This is a result by Bolobash exercise. This is a result of Bolobash in 1965. Says that for every n, at least t, at least k, at least 2, we have the saturation number of n, k, t, k equals to n choose k minus n minus t plus k choose k. Here, this guy is just the t vertex complete k uniform hypergraph. You have t vertices and all k sets in these t vertices form an edge. This is the second application. I'll leave it as exercise. Try to use Boloba's set pair inequality. Any question? It's about time today, so we will wrap it up for today. And next time, we will recall Sperner's theorem and see some application of Sperner's theorem, which is about this Boolean posets. Then we will define formally, extending this notation to a posets. So Boolean poset is a special type of posets, and study Dilworth's theorem. Okay. Any question for today?